Hi, everybody. How you doing? Welcome to the Virtual Night Sky, our version for March the 23rd, 2022. I wanted to just sort of invite everybody to kind of celebrate spring with us tonight. So that's going to be part of our program. The spring equinox was a couple of days ago. We'll talk about what that is and what that means and how it works. We're also going to dance around the sky. We're going to just kind of look again, take another look at all the bright stars in the sky this time of year. It's really is a spectacular time of year to get out and look at the night sky, actually sort of observe and see things. There's lots of things going on up there. And I'll be kind of like talking a little bit about sort of what to look for, but we're also going to talk about distances and the depth of space tonight. And that will follow along some of the things we've been working on over the last several sessions. And then I have a really wonderful guest tonight, and we're going to talk about a very unique part of our night sky that is up right now. It is visible to the unaided eye, a little bit hard to see, but there's a very special nebula, star forming region. We're going to learn a little bit more about that with a guest that I'll bring on about mid-show. A couple of events coming up. We got a couple of little short updates on some missions that we're following, and that's how we'll use up our hour. And I really appreciate everybody coming. If you've been here before, if you've joined us before and just a regular, welcome back. And I'm just really glad that you guys are kind of viewing the show and taking it very seriously, and that's really good. If you're new to us, we do this every other week. Maybe this is the first time you've watched. Maybe you kind of watch often enough, but we try to change things up every week. It's not the same thing. We take on a different topic, talk about a different part of the sky, talk about sort of relationships of different seasons during the year. And it really is sort of how we organize this. So you can come back every other week and learn something every other week and learn something very new. Let me introduce some of the people that are on board. And I always forget to introduce myself. So I'm Rick Alling, and I am a manager of outreach programs for the School of Earth and Space Exploration. Our operation on campus includes a gallery space for visitors to public to visit, and also a very special 3D theater where we do programming. Ever since COVID started, we've been developing this program and trying to stay connected to our visitors and our friends through virtual means. And but we are kind of heading back. We announce at the end of the show some of the first opportunities for the public to get on campus, visit us, see what we do. It's going to happen. We promised it in the spring, and we're going to make it happen. And so I'll tell you a little bit about that later. Always joining us on the show are some really wonderful students and staff members that have helped put this together and have been with us the whole time. So I always like to thank Kim Baptista for managing the webmaster part of this. She gets it organized, she gets the communication out, and she's working those controls that make this a program, a seamless program for you to watch for an hour. Also, my colleague Meg Hufford is always here, always a great advisor, always on board, and she and I together have with many student workers, we run the programs that are at the center, at the ISTB4 is our building on ASU campus that people can come visit. Two students are with us tonight, Alex Blanche, you've seen him every single show since we started, and a newbie, Armandala, is with us, and they're going to work in the background, kind of help answer your questions as we go along, and I'll tell you a little bit about that in a minute. And then we also, Alicia Hyatt is with us. She was a former student, now she's staff, and she's going to help with our program tonight. So all of that is the people that make this happen, and we thank you for joining us. Thank you much. I mentioned question and answer, and so there is a question and answer button on your computer. And you can just punch it, and it's for questions if you want along the way. If you hear something that you want to know a little bit more about, working those questions are the students, and they can answer them right away. And sometimes we'll bring questions to the whole group. So we'll bring them forward and answer them live during the program. So don't be afraid. Give us some comments, give us some questions. We like to do that. We like to entertain. We also use the transcript. So there is a live transcript, and you're in charge of that. You can have it on your computer, or you can have it off. We run it anyway, and so that's up to you whether you want to leave the live transcript operating. With that, let me just kind of get started. I think about a week ago, 2 weeks ago, I kind of like brought this map forward, and I'm just going to sort of review. Sometimes I like to do things twice in a row just so we remember. This is just a star chart. Excuse me. It covers the middle latitudes of the sky. So it's not the polar regions, not north, not south, but it covers the whole sky. And you can see right across the middle of this thing is the equator. That's the Earth equator projected out into space, and you sort of see the stars in the background, sort of what they would look like from the Earth, above the equator over here, down below the equator below that. And this curvy line that sort of like rises up on the sort of left side of the screen and then comes down and lowers. That's actually the path of the sun against the background of fixed stars. And what I want to do, I'm just going to zoom in right on the middle area here. Let me move it tight. And then I'm actually going to draw on the screen a little bit so that you can see some of the stuff going on. Let me get my pencil. And so what you're seeing here is this is sort of the path that I was talking about, sort of this line that goes up like this. And you can see it's actually marked in days. And what happens to us here is that we can see the sun is actually sort of right here. I'm trying to get some color on the screen here. Let me see if I can do that. Maybe I'll use yellow. So the sun essentially is right here in the middle, right where all of those things cross, right in the middle of the screen. That means it's following this path. It has moved from sort of the southern, just south of our equator. It crossed the equator 2 nights ago. That was on the day of the equinox, and then it sort of is going to just keep moving in this direction over the next several days. And just you can see, actually, I think you can see on the screen, if it's clear enough, there's little tick marks. Each one of those is a day. So that's how far the the sun moves against the background stars every single day. And then again, this is the point of the equinox. Today, we're 2 days later, so the sun is about right here. And then what happens is the sun will start to sort of swallow up stars in this part of the sky. As it moves in the direction to the left, right? The stars that are over here very close to the sun will just sort of melt into the sunset. They'll just become invisible over time. And so you won't be able to see those. The stars on the other side of the sun over in this direction are morning stars, and they become visible as the sun moves in one direction. More and more stars to the right of this scene sort of start to become visible in the sky. And so the equinox is essentially the path of the sun moving from the south to the north. But what's interesting is, let me just kind of point out the constellations that it is in right now. Back when this sort of whole thing was started, the idea of the zodiac, in fact, I can show you here. Let me just change color a little bit. This right here, this sort of lines that come down like this, is the constellation of Pisces, Pisces the fishies. Excuse me, I am sorry. I'm just sort of getting a little cough. It's probably the spring, right? And this over here is the constellation we call Aries. There's other stars that come down this direction here, Aries and Pisces. Back when this whole concept of the layout of the zodiac was formed, and people started to understand this movement of this sun through the background of stars, springtime was right here. That was it, sort of in this particular part of the screen. The spring was also the first day of Aries. The sun basically not only crossed the equator, but also moved from Pisces into Aries. And all of that happened at the same time. And I'm not going to sort of promote astrology right now, but this notion that you can sort of understand the sun moving against a background of fixed stars and how they move through this 12 stations of these zodiac signs all the way around, and then kind of get to the same place the next year. That was actually sort of very special. That was actually a level of science that was developed during Greek and Roman days. And they understood this was going on, even though the sun was there and you can't see these constellations. When the sun is in these constellations, they could interpolate. They knew how these sort of things worked. So why is it that now the sun crosses the equator and we're well into Pisces? I mean, almost a full 30 degrees behind, if you want. Well, that is an effect happening in space called precession, and we call it the precession of nodes is another way to say it. This particular point right here is called a node. When one object crosses a line and passes into the next level, that's a node. And so what the effect of that precession is, it's a wobble of the Earth, right? And it takes almost 26,000 years to complete a full cycle. So I want to make it very, very clear that the reason for the seasons is not that the Earth is wobbling. That's not what's happening. The reason for the seasons is that the Earth is leaning or tilted 23.5 degrees. And as it goes around the sun faces or favors the northern hemisphere for half of its travel, favors the southern hemisphere for half of its travel, and crosses these nodes twice a year, once in March and once in September. So that's the reason for the seasons. The precession is something else, and it will continue to move backwards, back into Aquarius and back, kind of retreating backwards through the entire zodiac. 25,800 years after that started, it will be that point, that node will be back between Pisces and Aries. And so people back then couldn't have predicted that. They didn't know that this wobble in the Earth was going to change sort of where the sun was at the equinox, where it was in the background of stars. But we know that now. And we call those epochs. So if you look at star charts, they will usually, if they're good star charts, they will tell you the epoch that they are intended for. The year 2000 was an epoch. So basically lots of star charts used that particular time as the location of all the stars and how all of that stuff fit together in the background on this particular star map. Those epochs change. And so if you need a star chart, if you're really looking for the exact location of the star, it does matter then. For you, it doesn't matter. You're not going to notice it. It doesn't change your seasons. It doesn't change when the sun crosses. It doesn't change your calendar. It doesn't change anything of that. It does change the background stars that the sun is in certain times of the year, during certain times of the year. The other thing I wanted to kind of just remind you, and we talked about this a couple of years ago, that if this particular side of my chart over in this direction is all about evening, then there's a huge, wonderful part of the sky here that we've gone over a couple of times, right? So these are the stars that are up right now. Sun sets, it gets dark, and this is sort of the central part of your sky right here after dark. All of these stars will sort of move in this direction over the hours. Eventually they were sun, but the time you want to go out and look at the sky right after dark, when it's nice and warm and it's nice, you're not too tired, and it's evening, sort of that 7:30 to 10:30 slot, that's when I do my stargazing. These are the stars that are up, right? So and that's really good to remember. I wanted to sort of show you this part of the sky again. Let me just change screens here a little bit. I'm going to go to, this is the planetarium program that I like to use. I'm going to tilt my screen up because I think this works a little bit better for your viewing. And this is the same part of the sky that I was talking about. What you're looking at here is everything that is within that green circle are stars that are available to you in the night sky right now. I think the time on this one, I'll just put it up there, is just about 8 o'clock tonight. So when we're done, you go out, these things are above the horizon. Now, depending on where you're looking from, you can see more stars or less stars. You can see the band of the Milky Way just sort of like trailing through this particular scene here. You probably won't be able to see that from Tempe, Phoenix, right? Just there's too much city lights and all this stuff. But if you were out away from the city, out camping or doing something like that, it's getting to that time of season where we can get out and explore. These are the stars that you would see this time of night. This particular program, because people ask, is called Sky Safari Pro in this case. There are versions of planetarium programs that are absolutely free and you can download them and they're all perfectly fine. I just happen to like this one, and it has a nominal fee attached to it. I think it was $19 last time I looked. So it's pretty easy to get in. I wanted to kind of just show a bunch of things going on here. So first of all, let me just kind of get a little sort of thing so I can draw here. Let me change my color to white. Over here, these are the stars on this side of the sky that are sort of melting into the sunset. And so eventually all of these will just sort of over time, they'll start to go away. You won't be able to see them in the night sky anymore. They're going away. These, as I sort of showed you or explained before, are in the sort of the central part of your view right now. And there's other stars that are coming into view. This is one of my favorite constellations, and the reason to point this out is it's just hitting the eastern sky this time of year. So here it is, spring. Here it is the equinox. Here it is March the 21st, and this particular star right here, one of my favorites, people ask every once in a while, I'm going to say this is one of my favorites, is called Arcturus. Arcturus is a great star because it sort of, it arrives in our evening sky in the east right at springtime. And Arcturus is the bright star of a constellation called Boötes. Boötes is the person sort of responsible for inventing the plow. And so there's always this attachment with this particular star, this particular constellation that's coming up, and agriculture. And so it arrives on the eastern horizon. We can look for it. You can kind of just see it. You'll probably be better off looking for it about 9 or 9:30 tonight. Very bright, orangish kind of star. And I always watch for it because it's a very special reminder that this is that time of year that we start to have to get our grounds. We plow, we till the soil, we get ready for planting. And Arcturus will move its way across the sky, be very, very prominent in your sky, sort of beginning about now and through the entire summer, into September, into October, and then it will start to set over on the eastern part of the sky halfway through the year towards the other equinox, the autumnal equinox. And it sort of signals the beginning of planting and the end of planting. And that really, I don't think there's any other symbol necessarily in the sky, with some other possible exceptions we'll talk about later in the spring, that sort of describes specifically a constellation that marks a season change, follows a schedule, an agricultural schedule, and then marks a season change at the end again. And so it's known for that. And that's kind of fun. I like to sort of see that happen. The other thing I wanted to go is I'm going to go back into this particular part of the sky. Let me just sort of stop share this particular one. I'm going to get a little bit better focus on this particular area of the sky. So if you can see here, the south is kind of to the south of the bottom of the screen there. And right above the southern horizon, not very far up, is an exceptionally bright star, and that's called Sirius. That's going to mark sort of the bottom of our scene. And then up sort of about halfway up the screen is kind of a yellow star that's called Capella, and that's going to mark the top of our scene. And we're just going to kind of take a look at this and really like deep dive into this one. Let me set it up so that I can sketch a little bit, and I'll show you what's going on here. We've reviewed this part of the sky several times over the since January. You might remember in January, Alicia kind of walked us through this part of the sky, and she was talking about star color. And certainly you can see, this is visible. You can go out and notice, especially in some of this, as I walk through it, I'll tell you where to look. You can notice differences in star color. So we covered that in January. And then a couple of weeks ago, Alex actually took on this part of the sky, and he was talking about stellar magnitude, how bright stars are and how the magnitude system works and all of that stuff. I'm going to take on this particular part of the sky and these same constellations. You should start to get very familiar with them now. And I'm going to talk a little bit about distance. Right? So there are two things that you can see as an observer. You can see, or three things. You can see relative brightness, bright stars, dim stars. You can see the color that Alicia was showing us a couple of months ago. You can sort of see that if you look a little deeper. You can also see how stars pattern, right? It's random, but they do tend to cluster together. They're little spatial relationships. How they appear in the sky stay the same all the time. They become very, very familiar. And it's those little shapes that over, years and years and years, over thousands and thousands of years, people have sort of named these constellations. Have, we can see them come back and repeat every single season at the same times. They develop meaning about when they appear in the sky and what's happening here. That sort of relationship to your year and the seasons, and that's really how this thing started. Those are readily observable things. The thing you can't see, you can't tell by looking which one of these is a close star or which one of these is a far star, or you just can't tell. And the depth is amazing. Let me just sort of give you some examples here. This is right here, this star right here is called Sirius. You guys sort of know that. That's the dog star. It's part of a constellation. I'll sort of just put the little stick lines in here that are part of what we call Canis Major. Sirius is only about 8.5 light years from here. 8.5. And so just give you a little sense of what that means. That is the distance light travels in 8.5 years. Light goes very, very, very fast. So these are vast distances. And so I'm just going to I'll make a little note here, say 8.5. Maybe you can see that on the screen. See that right there? This one up here, right, there's a triangle forming here. We've talked about this before, but if you look sort of up this way and then over this way to Betelgeuse and up this way to Betelgeuse, it forms almost an exact triangle in the sky. And so Procyon is this one up here. It's part of the little dog. Procyon means lead the dog. It's about 11 light years away. So 8.5 and 11. Those are bright stars and they're very close to us. But what about over here? This one over here, sort of the bottom, the knee of Orion over here, it's the star we call Rigel. It's a very bright blue star. It is about 860 light years away. There's a big difference, folks, between 8 and 860. And so what I'm saying is you go out to the end of your driveway, you go out to your backyard and you start looking around at the sky, bright ones, dim ones, and all of that kind of stuff. You really can't tell. It's not like you can say, oh, that star looks like it's way, way out there in the distance. In fact, Rigel is a very large, very, very powerful, very, very energetic star. And it's giving off a lot of light. And so that's why it can be as bright as it is, in your night sky, even though it's a great distance away. Everybody, one of my favorite stars is Betelgeuse, the sort of red one up here. And it's much closer than Rigel. It's about 500 light years away. So 860 is the lower part of the constellation. 500 light years from us is Betelgeuse. And so really, when you start to think about sort of what would Betelgeuse have to be as bright as it is and still be 500 light years away? Well, it's a giant. It's huge. The size of Betelgeuse is about the size of the orbit of Jupiter in our solar system. So it's a really, really large star. It's one of the first stars that in telescopes, as telescope technology got better, that they could actually see the shape of a star. Almost our stars just look like a point of light. They don't have any sort of circular sort of shape to them. Betelgeuse was one of the first stars that telescope operators and astronomers could actually see that it had size. And so those are sort of what that looks like. Within the belt here, and I'm going to later in the program, not very long from now, we're going to take a little break, and then I'm going to fly you out to Orion, just sort of as a little fly out. But the two belt stars that are on each side, not the one in the middle, but the two belt stars. Let me see if I can bring that forward a little bit. This belt star here is called Alnitak. This one over here is called Mintaka. So sort of you have Mintaka, Alnitak. Those are actually approximately the same distance from us. Roughly, they're about 800 and about 900 light years away. And so they're kind of like, if you want, they're in the same part of space. From those produced stars, they sort of not only share a position in our sky, but they share space. The one in the middle, though, is actually way, way out there. This one's called Alnitak, and I'm sorry, Alnilim. And that one is, if you sort of have a note here, let me just sort of like look at it, 1976 light years away. So to you, some people even call this the constellation Orion. It's the belt of Orion. It's those little three distinct stars. Next time you go out and look at them, right? Think of the two at the end being sort of, fairly close, distant, right? 800 to 900 light years away. And think of the one in the middle as being more than twice the distance to that star. They look the same. So what does that tell you? What do we have to think about that middle star? Well, of course, it has to be just really, really intrinsically bright. Where it is in space, it must be pumping out a tremendous amount of energy to be more than twice the distance and be essentially the same brightness to you. So I just wanted to, this is really the thing I wanted to share with you the most tonight, is that to really understand the sky, when you start to sort of see these familiar constellations, it's kind of fun to sort of just dig a little deeper. Find one of these planetarium programs, find a little star chart, find something you want to kind of look at, but just dig a little deeper and find out more about them. The other thing, I'm just going to kind of just give you the things to look at again, just so we can talk about that again in this particular part of the sky. So I'm going to delete that screenshot and just give you sort of just the whole series of things to go look for, because this is a really good time to do this. In about 6 weeks, all of these stars, all these constellations are going to be further and further into the west. And then in about 2 months, they're not going to be prominent in your sky anymore. We're going to lose them. So this is the season to look at this particular part of the sky. Let me just review the constellations you have to look at. This big guy here, we've talked about it a lot. We're even going to talk about it later tonight, is the great constellation Orion. Orion, sort of here, it includes stars out here. Some people sort of see this little thing out in front of him as like a bow and arrow, right? He's a hunter after all. He's the great hunter. And but actually, I sort of like, from the ancient star charts, they depict this as a lion skin. So lion skins would be used as protection. And then you can also see with Orion, there's very distinctly, if it's sort of like have a nice clear night, you can see his upper arm sort of like rising up above. So think of the two stars at the top of the body as Betelgeuse as a shoulder. And then this one is called Bellatrix. Bellatrix is another shoulder. And then you have, of course, the belt stars that sort of separate the top from the bottom. Rigel, again, is the bottom star. Looking at Rigel and Betelgeuse together in the sky, that's how you really get this really wonderful sense of color between stars. And then the one down here in this corner is sort of like a less known star. It's called Saph. Saph means point of the sword. That makes sense, right? And so really a lot of people, if you can see a little bit better, and this is not so hard to see in the city, you have the belt in the middle, and then this little thing, it's kind of like a knife or sort of little area of Betelgeuse that kind of hangs down like this, and people have sort of interpreted that as his sword. So he's holding this lion pelt in front of him, maybe a club over his head. Doesn't seem as much like as a hunter, as a warrior, but that's really Orion. And he's standing upright. He's in the southern part of your sky. He's easy to make out. He's really easy to see. Just above Orion is the constellation Taurus, and the face of the bull is over here, right? And the horns of the bull kind of stick out this way. And you can almost see a little action going on here. It almost looks like the bull is charging, right? And Orion is kind of ducking underneath it, ready to club him in the head with that big, huge club sticking up and guiding him over with his forearm and that thing. And so there's a little action going on here. Taurus is fairly easy to find. It's an oranger star. I mean, once you found Orion, just kind of look up and a little bit to the left. And there's a definite little V shape here. The V shape that sort of forms the face or the head of the bull is actually an open cluster. It's a group of stars that are sort of all related to each other. And there's 50 or 60 or 70 of them there. It's like a loose cluster, but in a binocular, you see more than just the little V shape, but you start to see like many, many, many more stars. And it's really fun to look at. So I kind of encourage you to go look at the face of the bull, look at the Hyades is what we call those. That little cluster is actually only about 70 light years away. So there's like a little kind of clump of stars about 70 strong, about 70 light years away from you. So you can sort of see them. Taurus is one of the signs of the constellation. And then the next one in order is Gemini. And those are the twins. And I'll sort of like just give them sort of little bodies coming down here like this. Brothers standing next to each other. The twins were on the good ship Argo when they were sort of like the Jason and the Argonauts, remember that kind of stuff? And they were searching for the Golden Fleece. And then there's another wonderful story about the twins that I sort of like, is that they sort of were on board this ship, and the ship was in the fog, and the fog was problematic for sailors because you couldn't really see where you were. Everybody was on high alert. They're all on the deck, and they're all listening for the waves breaking up against the shore, because for goodness sake, you didn't want your boat to drift too close to the rocks or too close to the shoreline when you're deep in fog and you can't really see what's going on. So you can imagine this there. It's crystal clear. There's no movement to the sky. And people, and the sailors are yelling out, and they're listening for their echo. Because if they can hear their echo, they're in trouble. So they sort of yell out, and they're listening for that shoreline. And while this was happening, a really funny thing happened. Have you ever heard of St. Elmo's fire? That's a sort of it's an atmospheric condition that puts in static electricity. And it actually runs little sort of electric charges that you can see up and down the masts and around the sails of a boat. And this little charge came down and sort of circled the heads of Castor and Pollux. And so sailors still sort of revere that. There's something special about these twins, and that they were on that boat, and that they were sort of like part of this adventure. So that was really pretty cool. So those are fun to look for. So the twin stars are there, Taurus and Castor and Pollux. And then let me just sort of finish out. Orija is the charioteer. He's up here. And this particular end of the bull's horn, where it meets Orija, the charioteer, there's a star that actually shares two constellations. This happens every once in a while. It's called El Nath. I think most people believe it sort of belongs to Taurus, but it's sort of it is a star that is sort of in both shapes. So El Nath is a really kind of important star in science too. Maybe we'll talk about that some here. And then again, sort of this triangle that we talked about. Triangles is an asterism. It's not a constellation. Betelgeuse is part of it. That's a bright star in Orion. Sirius is this one right here. That's the dog star, the big dog. Procyon is right here, and that's the little dog. I'm going to just do a little eraser here because I want to show you something about Procyon. Let me check the time. Oops, I got to get moving. So just one quick thing about Procyon, and then we'll go. This is the bright star right here, and that is Procyon. The constellation actually sort of like goes like this, and then up to this star, and then over here. And if you can see all three of these stars at the end here, you've got great seeing conditions. Let me erase that because I just got all the lines in the way. So yes, Procyon, you can see it for sure. If you can see this next one over, then you got a pretty good night sky. If you can see this guy, you've got a really good night sky. And if you can see this one, so there is a diminishing sort of stars of brightness. If you can see all four, you know your seeing conditions are really, really good. So look for Procyon, easy to find because it's a corner of the triangle, and then kind of sort of just see if you can kind of guide yourself to the rest of them. And that's a really good measure of how good the sky is. Then you can start to look for other things, but sort of start there. Maybe your adventure starts there, and you sort of see, okay, this is a good night to look, or there's a hazy, or it's not so good, or too bright, or those kinds of things. You can use the sky to do that. Okay, that's all I have time for our star walk today. But we've been covering this part of the sky for a while, for lots of good reason, because it's an amazing part of the sky, and you should take advantage of it and take a look at those stars. And we really encourage you to get out and do that. We're going to take a little break. And so this is where we'll kind of get to some of the questions that you might have had as we were kind of going along the way. We have a little poll for you. And then when we come back, I'm going to introduce you to our guest for tonight. We're going to dig a little bit deeper into the depths of Orion. Okay, let's take a break.
Thank you so much, Rick. I'm going to go ahead and launch our poll question. Let's see if we were paying attention here. What does the vernal equinox mean? Is it the first day of spring, approximately equal day and equal night? The sun moves from the southern hemisphere to the northern hemisphere, all of the above. Go ahead and cast your votes. And don't forget to leave us some questions down in the Q&A if you have anything that you want to know more about. So feel free to drop those in the chat, or I'm sorry, in the Q&A.
I love this
going
because
back,
some people jumped on the first answer, right? And then they say, "Oh my gosh, there's an all of the above." Yeah, okay,
I
I
know
get what I see how people work. Okay,
it's looking like 85% of us got that right at all of the above, 84%. So
super
we're
cool.
pretty much there.
Were
All
there
right,
any
I'm going to end
questions?
this poll. None that have come up so
Oh,
far, but maybe we'll save those for after our next segment. Dun, dun, dun.
we got a little dud of an audience, so I'm going to have to just remind you again. So there is an opportunity for you to kind of just ask and interact with us along the way, and so please take advantage of that if you can. I think that would be it's kind of fun to do. I'm going to let me see if I got my things set up right here, and I'm going to sort of use this as an opportunity to introduce our guest speaker tonight. I'm just really super pleased to have Alejandro Oliveira, and he'll introduce himself. I know him to be a graduate student. I know him to be in our program, and has a wonderful mentor, a professor that is revered in our program, named Sanch, and we call her Sanch. And so but while I'm kind of introducing Alejandro, I wanted to play a little game with you guys. So on the screen, you recognize this. You see Orion, the constellation, right? And so what I'm going to do is just center everything just right. And then I'm going to fly into the constellation. And what you're going to see is that some of the stars will start to move. And the first one you'll see is the upper right corner, the shoulder, will actually start to, oops, one quick thing. Yeah, no, I did this right. It'll start here in a second. And it will move by us because it's closer than the other stars. Did you see Sirius kind of get out of the way? So, and then as you go out here, you can start to see if you have the ability to fly. You have to use your sort of either tools like this or your imagination, because Orion now doesn't look like Orion, but we're seeing some of its inner parts. The exciting parts of Orion are starting to come into view. This is what I was getting at today. Sort of, you should start to understand the distance to these stars and the incredible depth they have. It's just another adventure. As I get a little closer here, I'm going to stop right here and just turn it over to Alejandro. You see in the middle of the screen here, just a big, huge cluster of stars and some cloudiness. There's some little kind of cloudy parts of the screen. Those are very important. And Alejandro is going to kind of introduce us into what that means. So hello, welcome to the screen.
Yeah, hello, everyone. My name is Alejandro Oliveira. I'm a graduate student here at ASU working with Sanch Professor Sanch Potaker. And I'm happy to be here. And let me go ahead and share my screen. So today, we just want to make sure everyone can see this. Rick, you can see this?
Yep, we're good. Yep.
Okay, sounds great. Yeah, so today I'm going to be talking about star formation, the Orion Nebula, and how it all relates to my research on galaxy evolution. So first, I just kind of want to clarify what exactly is a nebula and why are they important. I like to think of nebulae as just a bunch of gas and dust that's filling up a volume of space, and they kind of emit light. And they also offer some of the most beautiful images I've ever seen of space. Here's one in particular. It's called the Lagoon Nebula. This is shown in the optical range of the EM spectrum, and it was taken using the Hubble Space Telescope, which is a really great imaging telescope that has revealed a lot to us. But why are they important? So a nebula is important because it's often called a stellar nursery. It's the birthplace of stars. And why are stars important? Stars are important for a large amount of reasons, but mostly it's because they give life and energy to the planets around them. They provide information on the elemental makeup of the universe through their use of spectra. And important to me, they are crucial to galaxy growth and formation. So by observing star formation happening in other galaxies, we learn a lot about how our star, the sun, came to be, which is something we do want to know about, as it is our host star. Next, I'm going to quickly review the process of star formation because it is very important to what we're going to talk about later. So first, you start off with kind of this clumpy cloud. And by clumpy, I mean that there are certain parts of it modeled here by these darker regions that are denser, that have more mass. So if you have a certain volume and you fill it with certain mass, it has like a density. And if you put more mass into that, it's more dense. So these areas are denser than the lighter gray areas. And when you have more mass, you have more gravitational attraction. So with more gravitational attraction, you can pull more things in. And so in this little region here, you can see that the little clump there is starting to pull gas inward. And what this eventually forms, once you get enough gas, is a spherical form of gas called a protostar, which is not yet a star, but it's going to become a star. And it has an accretion disk around it, which is basically just a lot of gas that is going around and around this protostar that will eventually collapse onto the star. And once you have enough of this gas, you gain a lot of gravitational potential energy, which then is translated into heat. It's that heat is the energy is converted into heat, so the gas starts to heat up. And this is important because in order to be a star, you must be fusing hydrogen into helium in your core, and it takes a lot of energy to do that. And energy corresponds to temperature. So the higher your energy, the higher your temperature, the higher energy, and then you can form, you can fuse hydrogen in the core. So eventually you form a star. And so how does that all connect to the Orion Nebula? Well, the Orion Nebula is a place where lots of star formation is occurring. You can see a lot of stars here, lots of gas, lots of dust. There's a lot of fuel to form these stars. So what's actually happening in Orion though? I'm going to kind of zoom in on this image to get a closer look. And by the way, this image is from the Hubble Space Telescope as well, which is why it looks so nice. If you zoom in, you can see that this little area right here, this little cluster of stars, there's kind of this region right there. What that actually is something called an H2 region, which is formed from several massive stars called the trapezium cluster. What exactly is, and that's kind of like that astronomers like to use. So I try to really explain what these things are. And I think of it as this area of ionized hydrogen gas, but even that is a little complicated. So what exactly does that mean? So you have here neutral hydrogen, which is just called H1, which is just a proton with an electron orbiting it. Okay, if you give it enough energy, and it has to be actually a lot of energy, the electron can actually escape the electromagnetic attraction with the proton, because the proton's positive, the electron's negative, so they want to be next to each other. But if you give it enough energy, the electron, it can actually escape and be free of the attraction with the proton. In this state, it's called, when hydrogen does not have an electron, it's called ionized hydrogen, or H2. So an H2 region is just a region of space filled with a lot of gas in this state. And like I said, it takes a lot of energy, and that's important because to get hydrogen in this state, you need lots and lots of energy. And in nebular clouds such as Orion, you can only obtain high energies like this from O and B type stars. So stars have classifications to them. You can see them here, but the ones that are important to Orion in this case, and the H2 region in Orion, are the O and B type stars. All H2 regions are made from either an O or B type star, or a multiple of them. So O and B type stars are massive and blue, and they're very high in energy. So they emit a lot of light in the ultraviolet part of the electromagnetic spectrum, which is a high energy part of that part of the spectrum. And Orion has a cluster of O and B type stars. That's what the trapezium open cluster is. It's about 4 to 8 stars that are O and B type, and they create this H2 region. So on this image here, here's the optical version of it, taken with HST once again. But if we shift to the IR part, the infrared part of the electromagnetic spectrum, which is a little bit longer wavelengths, you can see past this dust, and you can see that there's a bunch of stars here. So those are the stars I'm talking about right there that form the H2 region. But how do H2 regions, because I was talking about star formation earlier, how do H2 regions connect to star formation? Well, O and B type stars form H2 regions, like I said, and they emit, these types of stars emit very fast moving stellar winds that compress gas. And why is the compression of gas crucial? Specifically, this gas also has to be molecular hydrogen. And I won't go into that right now, but just for your information. But why does it need to be compressed? Well, if you remember back to my diagram here on star formation, it all starts with the clumpy cloud. So if some of that gas is denser than the other parts of the gas, it can start the process of going through to make a star. So in a way, H2 regions drive the process of star formation. And star formation is something we really care about as astronomers because it's how galaxies are formed. It's very crucial to how they're formed. But what else can we learn from the Orion Nebula? If you have an image like this is an image taken from an at-home telescope, actually by my advisor with her telescope. You can see that part of the image is green and part of it is red. Why is there that difference in color? That's something we're going to explore here in a little bit. But I just want to say, if you have a telescope similar, it doesn't have to be a 6-inch like this. It can maybe be a little smaller. You can actually go out and take an image of the Orion Nebula yourself and maybe get something like this. But yeah, so back to the question is, why is there this difference in color? Well, if you use an instrument called a spectrograph, which breaks light up into its different components, much like when you hold a prism to like the sun's light and the rainbow comes out, that same type of idea. If you do that and observe Orion, you get what astronomers call an emission line spectrum. And that's what I show here. So let me explain what a spectrum is. So on the x-axis, you have wavelength, and the wavelength of this spectrum actually corresponds to the optical part of the electromagnetic spectrum, which is the part of the spectrum that we can see with our eyes. And on the y-axis, it's basically, you can think about it as the number of photons we're receiving of a certain wavelength. So the higher a line is, the greater height it has, more photons are received of that certain wavelength. But what is an emission line, right? I haven't really explained that. An emission line is basically the opposite process of ionization. It's when a free electron that's roaming around loses energy and recombines with the nucleus of an atom. When it loses energy, it's in the form of an emitted photon at a certain wavelength that is then sent to us. And that's what we see, right? Photon is light. So that's what we are seeing with our telescopes. And that's how we get spectra like these. So if we compare this spectra to the image, we can see some interesting things. So if you put the spectrograph over this part of the Orion image, nebula image, you'll get a spectra that looks a lot like this, where this specific emission line right here, it's actually an O3 line, which is when oxygen has lost two electrons have been ionized. You can see that you'd get a spectrum like this, and the oxygen line is a lot higher in height than this red line over here, which is called H alpha, hydrogen alpha. When you have, so in this image, in this green part of the Orion Nebula, you'd see something like this. If you moved to the red part of the Orion Nebula, this spectra would actually change. This height of this green line would actually go down. And so why that's important is because whichever line is higher will be what color you're seeing in the spectra, in the image. So in this part, because the green line is higher, you're going to be seeing more green light. But then the other parts where there's more of a red pinkish, you'll be seeing more red light because you're receiving more photons from that specific transition. So next, I just want to talk about spectra and their uses and kind of connect it to my research. So I use spectra a lot in my research, and in general, they're very crucial to astronomy because they reveal to us what the universe is made up of and can also tell us about the rotation of galaxies and a lot of things like this. I always appreciate spectra so much because they're just kind of like the key that unlocks all the information. So I look at H2 regions, and H2 regions exist, like in the Orion Nebula, exist all over the universe. And they're usually in bright blue star-forming regions of galaxies. And here's just an example. So this is the galaxy NGC 99 in the R band, taken with the VAT telescope. the in the red parts of this image here are all the H2 regions I look at. There's about 14 of them. And for each one, I have spectra. And with each of the spectra, I can get a lot of information. Here's just an example of one of those spectra. But what I really care about in my research is looking at the metallicity of these regions. Now, I kind of just said a really funny word, so I'll kind of explain what that is, what metallicity. Metallicity, symbolized by the capital letter Z, is just a measure of the amount of elements heavier than hydrogen and helium. So in the astronomer's world of things, any element that is not hydrogen or helium is considered to be a metal. It's kind of weird to think about, but that's how astronomers work. So that's where the name metallicity comes from. So in this spectra here, all of these lines marked here that don't have an H in front of them, that are not hydrogen, are considered to be a metal. And actually, there's a lot that I haven't marked, but there are a lot of other lines here, the smaller ones, that are not as strong. But why do we care about metallicity? Well, metallicity reveals to us the history of the gas that we're seeing. So if you have a high metallicity, that's telling astronomers that the gas that we're seeing has been recycled and used a lot and has been a part of the process of star formation for a while. If you have a low metallicity, that's telling us astronomers that the gas that has been used, that we're seeing right now, is kind of new, untouched, and it hasn't really gone through the process of star formation. And this is important because it lets us look at the history of the gas that is fueling the growth and evolution of the galaxies that we care about. And one major question in astronomy right now is how do the galaxies we see now, how have they gotten here, and how are they going to evolve in the future? And that's what my research is basically about. So that's all I really want to talk about. I have some time for questions right now. And yeah, thank you for your time.
Alejandro, that was great. Very, very, very detailed and very understandable. I love the way you've laid that out. And so
thank you.
And I can kind of sort of tell you're excited about what you work on, which is
yeah, I really do like it. Yes.
And you were an undergrad at Berkeley, right? And then chose ASU, is that right? And so why here? Why ASU? What made us stand out as a place you wanted to kind of do this research?
Yeah, for a lot of reasons. There's a lot of reasons. One, I really love the department and everything, the message of the department, the idea of exploring not only what we see above us, but what we see, what we live on. Another reason was that the amount of outreach that you and a lot of your colleagues do. I love planetariums. They're kind of what got me into astronomy.
That's great.
And yeah, I really wanted to be in a department that focused on outreach and getting science out to the public. Because I think that's a very important thing to do.
Good. I wasn't fishing for that answer, but I appreciate it.
No, that's my honest answer. Yeah.
That was very, very good. Okay. Alicia and team, what do we have? Do we have some questions? I see something in the thing.
We have a lot of great questions.
Oh, good. Exactly.
Yeah. So one of the ones that came up a bunch, in fact, we got kind of a similar question from both Mike and Elizabeth. Where these original gas clouds you're talking about, where do they come from? A lot of people want to know how those originally come about. I think you kind of touched on this.
Yeah, that's a really good question. So in general, we believe that the gas clouds come from areas like outside of the galaxy, above the galaxy, way far. It's called the intergalactic medium, which is a space between galaxies, and there's just a bunch of gas there that, due to gravity from the galaxy, will fall down and then form these stars. Now, on the question of why it's clumpy, that's a more complicated question. I don't know the origin of all density inhomogeneities in the universe, but I think it basically has something to do with the CMB, which is the cosmic microwave background. And we've noticed that on tiny scales in the universe, things are just not the same in terms of density. Now, where these come from, that is not a question for me. I'm not a cosmologist. So yeah.
Stay in your lane.
Even as a cosmologist, I don't think many people know that answer.
Yeah.
It's just kind of what it is. The CMB has always been non-uniform.
Right.
We had another question from Stuart asking, in these protostars, if there's not enough gas available to reach that stage of becoming a star, what happens? What do these protostars become?
Yeah, that's a really great question. And that actually goes into the other side of astronomy, which is like exoplanets kind of. But those stars, those protostars are basically called, like, people do call them failed stars, but they're called basically brown dwarfs, which are things that are a lot like a lot like Jupiter in a way, just a lot hotter. But the reason they're not considered to be a star is because they're not hot enough to fuse hydrogen, and that's just like the one absolute rule that you have to be a star. So most of them will probably become like something like a brown dwarf. Yeah.
And then from Justin, when you're talking about the color spectrum of star and nebulae, how do you determine whether or not that's accurate?
Yeah, that's a great question. Um, so so in like a lab, we know that what's actually happening here while we're seeing these emission line is an electron will move from a higher energy state to a lower energy state in the atom, and that jump either up or down corresponds to a certain energy and wavelength. And these transitions happen no matter what. So we know the known place they should be. So when you get a spectrum, you should see a line at that one wavelength, and we have like a whole list of wavelengths and like what element and transition it corresponds to. And basically, in my research, a lot of what I do is like matching up where that spectrum should be. Yeah.
Well, thank you so much. There are still a lot of questions in the Q&A, so if you want to hop in and type out the answers, but I think we're going to move on to current events with Kim and Alicia, and then we'll wrap up our show.
Thank you
Thanks so much.
Thank you again, Alejandro. It was absolutely so
good
we'll
times.
have you back on. Good.
Yes. Thank you, everyone.
Yeah, we wanted to just so we've got 2 missions coming along, and both are going to launch within the next 4 or 5 months. And we've been following them for years. We want you guys to sort of just get a quick little update on 2 different missions. Kim will take the first one.
Okay, well, good evening, everybody. And it's kind of hard to follow Alejandro here. I'm going to try. As you guys may know from our talking music.
Yay.
Yay, current events. I feel like I'm doing a news broadcast. Yeah, so Artemis 1, we are anxiously awaiting for this to launch, to get scheduled. So the current state of Artemis 1 is it's in the wet dress testing phase. And what that means is that last Thursday, it rolled out to launch complex 39. It was a 4-mile journey, took 11 hours to get there. And then earlier this week, they ran some more testing. They powered up all the elements. And now we're waiting for April 1st through the 3rd, where they will place the fuel in the rocket, and then they will count down the clock to T-10, and then they will stop it. They will defuel it, and then they will make their final checks before they roll it back into the VB. And the reason we are essentially waiting for this launch to be announced is because, if you recall, earlier this semester we had Craig Hargrove on with us, and he has a CubeSat that was built here at ASU. He has that, it's one of the CubeSats of 10 that's on the payload for the Artemis 1. So we are very anxiously awaiting that. So that is currently what's happening, and we hope to announce when the launch will be and let everyone know so that they can join us in watching it happen.
A big milestone in the process. And these 2 pictures next to each other is amazing, because in that little suitcase on an airline is a spacecraft. And now it's up at the very, very top of that rocket. You see that sort of getting prepared to sort of like launch. And so it's part of that payload. And so I just think it's great. This is really a wonderful process to watch. And so we'll advise you when this thing goes and how important it is, and how this is going to work, when you're going to start to see the science. So good.
Yeah.
And then
just a reminder that LunaMap is the CubeSat that will map water deposits on the lunar surface to allow NASA to assess the distribution of its vital resources on the moon. So it's quite a critical CubeSat. So yeah, but so more to come on that. So stay tuned. So And I'm going to hand it off to Alicia, who's going to take it from here for the next
One more
one.
thing, it was also built, just to reinforce, in that building that's behind Kim right now. So that it's a spacecraft going to space that was built in our building. That's really cool. Alicia, got another update, another mission. What's going on?
I do 16 Psyche. So Psyche is the name of a mission as well as the name of an asteroid. And we are very excited here at ASU because we're a part of this mission. We're in charge of building this spacecraft, or in charge of, I guess, delegating who's building the spacecraft and getting it to Psyche. And so, as I mentioned, 16 Psyche is the name of an asteroid that's roughly the size of Massachusetts, and it lives between in the asteroid belt between Mars and Jupiter, excuse me. So it's an incredibly large asteroid. And the reason why we're so interested in this, not only because it's ASU led, but also because we believe this is the first time humans will get to explore what we think might be a planetary core remnant. And so what we think happened with Psyche was on its way to become a major planet, or to become a planet, I should say, when it was involved in a hit and run collision in space. And unfortunately, its outer shell kind of fell off, its outer crust, if you will. And so we were left with what we believe is an iron nickel rich planetary core. But we don't know. The only thing we know about Psyche is that it doesn't look anything like this. And so what I'm going to do now is play a video for you that talks a little bit about one of these wings or solar panels that we're building currently. So I'll go ahead and play that now. And this is launching in 2022, so August of this year. Keep that in mind.
Excellent. And so this is, Alicia, this is really new stuff, right? That's just testing that has happened just within the last couple of weeks. So this is we have a little video earlier. We sort of showed it to the audience about the spacecraft leaving San Jose and arriving at JPL. So this is one of those gigantic, clean room facilities at JPL where they can load the whole spacecraft in there and sort of test the deployment of those solar panels. Great to see.
Yeah, it's a real current event, Rick. It's really happening right now.
Really happening right now, and so important to ASU. And then it's especially important to me because we're actually, me and a team of students, we're building a life-size Psyche spacecraft in our building. We're just, as a model, we're not building the real spacecraft, but we'll be able to see the extent of those solar panels and how the sort of spacecraft comes to be. We'll be mounting that in the summer, getting ready for the August launch. So it'll be kind of fun to see. Well, thank both of you, Kim and Alicia, for getting us up to date. Always kind of, there's always some new things going on. I wanted to I'm just going to wrap here. I'm going to just announce a couple of events, but I wanted to first start with a thank you. 2 weeks ago, we don't hear me often do this, but I sort of made an appeal for everyone everybody to understand there's a way to just kind of, contribute to ASU. We still need those kind of contributions. We did Sun Devil Giving Day. It was actually on St. Patrick's Day. So that's a coincidence, not on purpose, but it was great and it was very successful. And we know many of our audience participated. So thank you very, very much for taking the time to do that and thinking of us. I think that's really, really great. A couple of events coming up is this weekend on Saturday. I didn't have a chance to sort of send Kim the announcement, but there is a little festival going on at Fountain Hills. For those of you that have watched for a long time, you know that we have this really wonderful relationship with the Fountain Hills folks. They're developing a little science center out there. It's an observatory and a planetarium. They're just in the beginning stages of getting the architecture done and all that stuff. And they're holding a little festival this Saturday, and it will be in the afternoon into the evening. You'll have to look at it. And they're just kind of celebrating their dark skies. After sunset, they'll have some star walking and some laser pointers and some people kind of showing you the sky. There's a couple of guest speakers. One of them is the director from Lowell Observatory, and the other one is yours truly, me. So I will be up in Fountain Hills and doing a little lecture. I'm going to talk about time and calendaring and that kind of thing, about astronomy and how it relates to how we sort out our year and our day. And so looking forward to that. Also on campus, on April the 9th, it's also a Saturday, kind of about 10:30 to 1, if I remember right, 11 to 1:30, something like that, right over the noon hour for several hours.
11 to 1. 11 to 1.
We are having an open house on campus. So this is your chance to come visit us, see what we're doing in our building. You'll see the Marston Theater finally for the first time, sort of in a couple of years. We'll do some 3D programming for people. And if you are looking for an opportunity to come visit us, see and meet us and see us do what we do, where we do it, that's the time. And so looking forward to that. April the 9th. It's a Saturday, 11 to 1 o'clock, open to the public, and everybody can come. Kim, do we have any other announcements? Is that it? I think we're ready. Oh, well, the next show, Virtual Night Sky, is 2 weeks from tonight. And in this particular one, we're talking about sort of citizens and science again. It's a topic we covered a long time ago. And just to prep you, just so you can sort of think about this before we get there, we're going to assign you, the audience, a citizen science project. And so we're going to tell you what it is. You're going to get instructions. You're going to have to go do it. You're going to have to sort of send us some information, and we're going to give you the results 2 weeks after that. So if you've wanted to get involved in science, you want to make practice of some of the things we've talked about over the last couple of years, this is your opportunity. So we've got a couple of guests that are working in this area, and I think that'll be a lot of fun. So we look forward to seeing you in 2 weeks. Is that it, Kim? Did I do it? Did we get everything?
You got it. So
Yeah.
this is the big thank you for the evening.
Thank you very much. Okay. Well, everybody, we always run over a little bit, and we ran over again tonight. So thank you for joining us. Come back and tell your friends, and come back and see us in 2 weeks, and we'll see where we go. Thank you very much.